Yeah, good morning, everyone. I hope everyone had a great week at JM. So it is my distinct pleasure to introduce Dr. Yuxi Chen, an esteemed researcher and assistant research scientist at the University of Michigan Department of Climate and Space Science and Engineering. Dr. Chen earned his PhD in Space Science and Scientific Computing from the University of Michigan, where he also completed a master's degree in atmospheric, oceanic, and space sciences. His academic journey, it began with a Bachelor of Science in Geophysics from the University of Science and Technology of China. Dr. Shen's professional career is marked by a series of prestigious positions, including his recent role as a senior research scientist at Boston University and an associate research scholar at Princeton University. His research experience is broad, encompassing advanced space plasma simulations, MHD with embedded particle in cell models, and the dynamics of Earth's magnetosphere. He has been the principal investigator of many NASA-funded projects, contributing significantly to our understanding of global mass and energy transfer rates from solar wind to the magnetosphere. Beyond his research, Dr. Chen is also dedicated to education and mentorship, having guided graduate and undergraduate students in their scientific pursuits. His contributions to the scientific community are further evidenced by his roles in journal refereeing and also serving in proposals panels for various NASA programs. Please join me in welcoming Dr. Yuxi Chen.
Good morning, everyone. Thanks for the nice introduction, and thanks for the GEM committee to invite me for this tutorial. Is my sound
closer to your mouth?
okay?
So and online sees your notes and you show that. So switch there. Oh, display. How do we do this here? Anybody knows how to do that on?
Sharing.
Yeah.
Sharing on Zoom.
Online sees this instead of that.
Maybe we need to change the screen share to Zoom. We need to find Zoom. Share.
I think. Yeah, it's better now.
Okay. Thanks for the GEM committee for inviting me to give this tutorial. I'm sorry. It's my great honor to share my knowledge and experience about numerical modeling of solar wind magnetosphere interactions. I will start with MHD models, but focus on the beyond MHD techniques. If I speak too fast, please remind me. Otherwise, you will have plenty of time for questions. This is the outline. First, I will briefly introduce the physical process that controls the solar wind magnetosphere interactions. Then I will walk through all the global numerical models have been developed to investigating the solar wind magnetosphere coupling process, including the fluid models and also kinetic models. I will also show some numerical scaling techniques that has been used to speed up simulations. Finally, I will use the MHD APIC model as an example to show the capabilities of the global kinetic models. When the upstream solar wind is southward, magnetopause reconnection can happen at the low latitude of the magnetopause. Reconnection opens the closed magnetic field line of the dipole field and transports the mass, momentum, and energy from the solar wind to the magnetosphere. When the MF turns to northward, magnetic reconnection can still happen at high latitude. Meanwhile, at the flank of the magnetopause, KH instability may develop. I want to emphasize that Ketch instability itself can be described by a fluid model, but the Ketch instability itself doesn't necessarily lead to the transport of plasma from magnetosheath to the magnetosphere, because even if you have vortices, the plasmas can still frozen in with the magnetic field lines. In reality, during the nonlinear phase of the Ketch instability, magnetic reconnection may happen within these vortices and lead to the transport of plasma from magnetosheath to solar wind. During this nonlinear stage, the boundary layer becomes very thin, so the wave-particle interactions can also diffuse particles from solar wind to the magnetosphere. Given this phenomenon, if we want to really self-consistently model the Ketch instability, kinetic model may be required. The structure between the magnetopause and the solar wind is a shock. In a fluid description, the shock is a laminar discontinuity. However, in reality, the shock is very dynamic. The shock is the source for the turbulent magnetosheath flow and what kinds of kinetic waves and some plasma jets. When these features arrived at the magnetopause, it may impact solar wind magnetopause interaction. For example, these jets or waves may trigger day-side reconnection. So for modeling the solar wind magnetopause coupling, the role of the kinetic shock should be taken into consideration. There are various tools for studying the solar wind magnetopause interactions. We can use the space-based observations, ground-based observations, and we can also use numerical simulations. In this presentation, I will focus on the global simulation techniques. We know the plasma in the geospace environment is collisionless. So essentially, almost all the physical processes that controls the solar wind magnetosphere coupling can be described by the Maxwell equation system. Can you see my cursor? Okay, maybe not. So all the physical process can be controlled by the Maxwell equation system. However, it is not easier, not trivial to solve this equation system. There are various ways to solve it. If we directly solve the phase space distribution for the Plasov solver, we can get the kinetic methods. However, as we will see later, these kinetic methods are computationally expensive. There is another class of method called momentum method. You can get the moments of each fluid from the Plasov equation. And instead of solving Plasov equation, you can solve these momentum equations. From the momentum equation of each fluid with some assumptions, you can get the MHD equations. This slide shows how we can obtain ideal MHD equations from the Plasov equation. The purpose is to show the assumptions behind this ideal MHD system. So from the Plasov equation, if you integrate this equation over the velocity space, you will get the continuity equation for each fluid. Similarly, you can get the momentum equation and pressure equation for each fluid. So far, there's no any assumption. It means this equation chain is valid for a system, for a plasma with any distributions. However, it is also difficult to solve this equation chain. Instead, with these assumptions, we can get the ideal MHD equation. What are the assumptions? First, if you assume the quasi-charge neutrality, you can get rid of the continuity equation for electrons. If you assume the electron initial can be ignored. You can get rid of the electron momentum equation. Instead, you get the Ohm's law. From Ohm's law, you can calculate the electric field. Furthermore, if you assume the pressure is isotropic, then the pressure equation for a tensor reduced to a scalar equation. With these assumptions, you can get the ideal MHD equation system. The ideal MHD equation is capable of capturing the global structure of the magnetosphere, like the location and shape of the boundary layers, like the Boshock and magnetopoles. The ideal MHD system can also generate and propagate all kinds of MHD waves and all kinds of MHD instability, including the KH instability. Even though the magnetic reconnection in an ideal MHD simulation is numerical, the ideal MHD model is still reasonably good at simulating the global response of the magnetopole reconnection. Since the ideal MHD do not contain any kinetic physics, it cannot get the local reconnection physics right. It cannot generate kinetic physics at the shock. That are the limitations of the ideal MHD. The capability of the ideal MHD equations are also limited by the numerical accuracy of your implementation. When we solving this partial differential equation numerically, we discretize the equation into a grid. And your discretization introduces numerical errors. After your discretization, the equation you solved numerically could be different than your original analytic equation. And the difference between these two equations are the discretization error. For example, here I show the discretization error for a very simple first-order spatial gradient calculation algorithm. We can see the error is proportional to delta x, which is the cell size times some spatial gradient. If your error is too large, your simulation may not give you the results you want. For example, it may suppress the KH instability. So we need to reduce the numerical errors as much as possible. The first way to reduce the numerical error is developing high-order schemes. What does it mean? It means you design some sophisticated interpolation algorithm to remove the low-order errors. For example, if you remove the first-order error delta x times something, you only keep the delta x squared error. Then you get a second-order scheme. The higher the order is, the more accurate your algorithm is. Another technique to reduce the numerical error is using a reduced cell size. However, if you reduce your cell size, your total number of cells will increase very fast and slows down your simulation. At this time, you need a technique called adaptive mesh refinement. It will reduce the total number of the cells while still keep the simulation accurate. In the next few slides, I will show you the power of the high-order schemes and show you a few examples of the AMR grid. These are some simulations performed by Batras. The first row shows the second-order simulation with different grid resolutions. This is the first row. The second row shows the simulation with fifth-order scheme with different grid resolutions. And as you can see, in the second-order scheme, there's no and this simulation simulates the flow around the magnetopoles. As you can see in the second-order scheme, there is no KH developed with in the second-order scheme with 1/8 grid resolution. You will not see it until you use a grid resolution of 1/16 Earth radii. However, in the fifth-order scheme, you can see the KH instability with a grid resolution of 1/8. It demonstrates these high-order schemes can reduce the numerical diffusion or dissipation and allows the development of KH instability with a relative coarse grid. In our field, LFM or Gamma is probably the most well-known model for investigating the KH instability. And you can see the development of KH at the flanks, very beautiful vortices. I want to mention in China, there is also a group. They developed their own global model for simulating KH instability. Just as we said before, if we reduce the cell size, you can also reduce the discretization error. However, your simulation cell number will increase very fast. Adaptive mesh refinement is a technique to allow you only refine the region where you are interested in, or the region where the spatial gradient is large, so that you can accurately capture the physics happens there, like at the boundary layer. In some place where the spatial gradient itself is very small, for example, in the supersonic solar wind, it is uniform if the upstream condition is steady. In such region, your numerical error is very low, no matter how large or how small your cell size is. So in such area, you can use a very large cell size. While the discretization error is still very small. For solar wind magnetosphere coupling simulation, we usually refine the error at the magnetopoles, as you can see from the right plot. MR mesh has been used by Batras, and it's probably the most important feature that most important numerical feature that distinct Batras from other numerical models. Now that we have seen some examples of ideal MHD and talked about some numerical techniques to reduce the numerical error in fluid simulations. Before we move on to beyond MHD models, I would like to have a few words about the spatial scales in a numerical model. In an ideal MHD model, there is no intrinsic length scale. Instead, there are two external length scales. One is the size of the body. It is determined by the strength of the dipole and the upstream condition. Another scale is the cell size. In an ideal MHD, the thickness of a boundary layer, like the magnetopause current sheet, is determined by the cell size. Its thickness is proportional to the simulation grid size. In another word, even if you can have a IDMAD simulation with very high grid resolution and with very thin current sheet, you cannot claim it is more physical than a simulation with a coarse grid, because both of them are decided by cell size instead of by physics. Hall MHD is different. The Hall term introduces the ion initial length. If you really want to resolve the Hall physics in your simulation, you need to resolve the ion initial length. So in a global simulation, you will need very high grid resolution. That's why a Hall MHD simulation is usually much more computationally expensive than an ideal MHD. Similarly, if you introduce kinetic physics into your model, ion kinetic scale or electron kinetic scale, and if you really want to keep this physics in your simulation, you also need to resolve these kinetic scales. Okay. Now let's see how we could expand or how we could improve the physical capability of the from the ideal MHD. In ideal MHD, we use Ohm's law that assumes the magnetic field line is frozen in with the ion flow. And we know this is not true inside the reconnection ion diffusion region. But even inside the ion diffusion region, the magnetic field line is still frozen in with the electrons. So if we assume magnetic field line is frozen into electrons, this is already a step forward for reconnection simulation. With this assumption, well, did I just delete one slide? Well, I'm sorry, maybe I deleted one slide somehow. With these assumptions, we get Hall MHD. In Hall MHD, we assume we use the Ohm's law, electric field equals minus UE cross B. This is very similar as Ohm's law in ideal MHD. Electric field equals minus U cross B. It looks like these two Ohm's law are very similar. However, the small difference introduces a lot of numerical difficulties. That is why in our community, there isn't too many global models that implemented the Hall term. And just as I said, in order to capture the Hall physics, you need to resolve the initial length in Hall MHD simulation, so it makes the simulation expensive. However, a lot of simulations have shown Hall MHD is important. Hall term is important for reconnection. With Hall term, you can get the patch track faster reconnection pattern. You can get the very important quadradipole magnetic field near reconnection site. So it is widely accepted that Hall MHD is probably the minimal requirement for simulating the local reconnection physics. And Hall term have been implemented into the Buttress model. Okay. So when we derive ideal MHD, we assume the pressure is isotropic. If we relax this assumption and allows the parallel and perpendicular pressure to be different, we will get the MHD equation, MHD system with anisotropic pressure. This has also been implemented into Buttress, but it has not been widely used for simulation, so I will just skip it. What if we do not assume the quasi-charge neutrality and do not assume the electron initial can be ignored? Then we will get this moments method. The right-hand side of the slide shows the equation system for the moments method. It looks similar as ideal MHD, but actually they are very different. In this moments method, we solve the continuity equation, momentum equation, and pressure equation for electron also. So you cannot use Ohm's law to get the electric field anymore. Instead, you need to solve the Ampere's law to get the electric field. This is the moments method. Based on how you solve the pressure, you can have different types of high-order moments method. If you assume pressure is isotropic for all the fluid species, and you only solve a scale pressure, you get the 5-moment method. 5 moment means it solves for the density, 3 components of velocity, and 1 pressure scalar. If you assume the parallel and perpendicular pressure can be different, then you get the 6-moment method. If you solve for the whole tensor of the pressure, you get the 10-moment method. In this moment method, since you solve electron and ion independently, in principle, you can have long mu oscillations. And because you solve the Ampere's law, you can also generate light wave inside this inside this system. This high-order moments method have been implemented into Buttress and Jekyll-2. Jekyll-2 have been applied to simulate small magnetospheres like Ganymede's magnetosphere and Mercury's magnetosphere. So far, no one has applied this model to simulate Earth's magnetosphere, but in the near future, we may see such applications. I want to mention one thing. In the time-moment method, since you solve the whole pressure tensor, it may significantly improve the reconnection physics. So you may get very great results from this time-moment model. Now that we have discussed this moment method do not directly solve for the Flash-Solve solver, do not directly solve for the velocity space distribution. If we solve the velocity space distribution, we get these fully kinetic models. Based on how we resolve the velocity space, we have different type of kinetic models. If we use a mesh, no matter it's Cartesian or non-Cartesian, to resolve the velocity space, then we get the full Flash-Wolf solver method on the left slide. If we use microparticles to represent the velocity space, we get particle in cell code in the middle. The third type of class is called spectral methods. You can use a spectrum to represent the distribution of the velocity space, and you solve for the changes of the spectral coefficients during your simulation. This type of class, in our community, this type of class, there is one such type of class. It is under development in Los Alamos, led by Dr. Gianluca. Since the first two types of class are more widely used, we will focus on this in the following slide. The Flash-Wolf solver, it is noise-free, better than peak. However, it is usually much slower than peak. Why? Because you need a mesh to resolve the velocity space. How many cells you need in each direction? Well, I would say maybe at least 20 in each direction. Then in order to resolve the three velocity component, Vx, Vy, Vz, you need a mesh of 20 by 20 by 20 cells. It leads to about 10,000 cells. This is 10,000 cells. I mean, this is for each spatial cell. For comparison, in a particle in cell code, we usually use about 100 or 200 microparticles per cell. So the number of velocity space cells per spatial cell in a Flash-Wolf solver is usually much larger than much more than the number of microparticles in a particle in cell code. That is why a Flash-Wolf solver is a Flash-Wolf method is usually slower than particle in cell code. This kinetic method doesn't sound like complicated, right? But why no one directly using this fully kinetic method to simulate the interaction between solar wind and Earth's magnetosphere? Because the limitation, because the large separation of all kinds of scales, and also because of the limitation of the numerical resources. Just for fun, this slide shows how much memory is required for simulating Earth's magnetosphere with a particle in cell model with uniform mesh. Let's assume your magnetosphere size is about 100 Earth radii in each direction, and your electron scale is about 6 kilometers. This is a parameter in the magnetosheath. And you need a grid resolution can resolve electron scale. So with these parameters, you need about 100,000 cells in each direction. 100,000 doesn't sound like a very large number, right? But remember, in a 3D simulation, it will lead to a cell number of 10 to 15 cells in the whole domain. If we assume you will use about 200 particles per cell to do the simulation, with some calculation, you will find you need about 10 to 10 gigabytes of memory for this simulation. 10 to 10, how large it is? I guess your laptop has a memory of about 16 gigabytes or 32 gigabytes. Of course, if you are using Mac, maybe you only have 8. And so 10 to 10 gigabytes is equivalent to about 1 billion personal laptop. This is just insane. We cannot use so much memory just for simulating the interaction between solar wind and the magnetosphere, right? So in order to make these kinetic models feasible for global simulations, we need to reduce the computational cost. That is the motivation for developing hybrid methods, hybrid models. In my opinion, there are two types of hybrid models. The traditional hybrid models treat the ions with kinetic method. by treat the fluid electron with the fluid description. In the hybrid model, since the electron is treated as massless fluid, you do not solve the you do not solve the momentum or the motion of electrons. So you can have the Ohm's law to get electric field. This hybrid method sacrifices the electron scales to get a huge speed up in the simulation, in terms of simulation speed. If you treat your ions with particle cell method, you get the peak hybrid code. This is the result from NGL3D. The NGL3D code is developed by Urban University. This is probably the most widely used peak hybrid code in our field. If you treat your ions with a Vlasov solver, then you will have a Vlasov hybrid model. The well-known Vlasata is a Vlasov hybrid code. The MHD with embedded particle cell model, MHD epic, it's also kind of hybrid model. It combines the efficiency of the global fluid code with the physical capability of the local peak code. Essentially, it assumes kinetic physics is only important in a local area of your simulation. You do not need to cover your whole domain with a kinetic code. Instead, you can embed the kinetic code into a global fluid model. This model is two-way coupled. It means at the very beginning of the simulation, the MHD code will provide the initial and boundary condition for your peak code. Then your two codes can update independently. After a few steps, you do the two-way coupling. MHD provides the boundary condition for peak, and your peak code overrides the overlapped MHD area. Recently, we expand the capability of the MHD epic model and developed the MHD with adaptively embedded particle in cell code. The adaptive means two things. One thing is you can use the peak code to cover a kinetic region of any shape. For example, in this plot, these black lines indicate the edge of the peak domain. And in this case, particle in cell code covers the dayside the subsolar point area, and also contains the flanks and high latitude. The adaptive A also means you can dynamically change your particle in cell domain during your simulation. This is important for a long simulation in which your boundary layers may move a lot. For example, for simulating a real storm event. Okay, so far we have walked through all the numerical models for solar wind magnetosphere interaction. And as we just discussed, the hybrid models already greatly reduced the computational cost. However, if you directly apply this hybrid model to the simulation of Earth's magnetosphere without doing any artificial scaling, you may find it still very computationally expensive. That is because the separation between all kinds of scales are still very huge. So people are using all kinds of scaling techniques to reduce the separation between the scales. The first well-known technique is to reduce the ion-electron mass ratio to reduce the separation between electron scale and the ion scale. A lot of simulations have demonstrated that the reconnection process is only weakly depends on the mass ratio. So in this plot, it shows the reconnection rate with all kinds of electron mass ratio. And as we can see, these dots are almost horizontal. It demonstrates reconnection rate do not depend on the electron mass ratio. So these techniques have been widely used in almost all the peak simulations for reconnections. Even after applying these techniques of changing MI-ME ratio, in a global simulation, your separation between the ion kinetic scales and the global scales can still be very huge. So in our MHD epic model, we decided to reduce the charge per mass ratio to increase the ion initial length. Here, I show a few examples with different scaling factor. And as you can see, the size of the well-developed FTEs do not depend on the scaling factor. It demonstrates the scaling factor do not change the global structure significantly. I want to emphasize one thing. In our MHD epic model, we always describe how we do the scaling, but in practice, as far as I know, most of other hybrid code also do the scaling in one way or another. In the flash data simulation, they do not do the artificial numerical scaling, but they usually use a reduced solvent density, for example, 1 mu per cc. Then it will also increase the ion initial length in the system. Okay, so far we have walked through all the global numerical models for the solvent magnetosphere interaction simulations. In the next few slides, I will show you the capability of this global kinetic code with MHD epic. This is the MHD epic simulation of Earth magnetopause reconnection. We use a peer code to cover the day-side magnetopause region. Since it's a peer code, we can study the electron kinetic physics. And as you can see from the picture in the middle, we can resolve the crescent both electron and ion crescent distribution near reconnection site. And since our peer code covers most part of the day-side magnetopause, we can also capture the evolution of the FTEs in the same simulation. Here I show the MHD epic simulation to study the onset of the reconnection and the expansion of the X lines on the day-side magnetopause. These figures are beautiful, but there is one problem have been bothering me for a while. Are they really physical? We do not know until we do some validation or by compare the simulation results with observations. So in recent years, I have started collaborating with Toshi. We are trying to compare the ionosphere observation data with MHD epic simulation output. Although the day-side reconnection happens at the magnetopause, but its product like the plasma can propagate to the ionosphere, and the food point of the reconnected field lines also convect in the ionosphere. So by comparing the signature in the ionosphere, we can get some information about what happens on the day-side magnetopause. In the left, this plot shows the polar world flow in the ionosphere from the simulation, from the observation in the top panel, and also from MHD epic in the last panel. We can see they have similar patterns. And if we calculate the expansion speed of this boundary, we also see the observation and the MHD epic simulation matches pretty well. So it gives us some confidence in the simulation results. By the way, I forgot to mention one thing. Most of the work, of course, are done by a graduate student, Wei Zhang. Since the shock is kinetic, it produces a lot of structures that are propagating towards the magnetopause, and they may change the solvent magnetosphere coupling process. So it's important to evaluate how important the role of the kinetic shock is. Here, I show an example from the MHD peak simulation. We use a peak to cover the shock area, and this is a quasi-perpendicular shock, but the Mach number is extremely high. It can happen at Earth, just unusual. In such case, we can see the magnetosheath becomes very turbulent. We want to evaluate if this turbulent magnetosheath will have influence on magnetopoles reconnection. Since this is a particle in cell code, both electron and ions are kinetic. So at the shock, we can see the reflection of both ions and electrons. In principle, we can study the physics of ion full shock and electron full shock in the single simulation. All right, that's all. That's the summary of my presentation. We walked through all the numerical methods that have been used for study solar wind magnetosphere interaction. And with MHD epic as examples, I show you what a global kinetic model can do. That's it. Thank you.
Hi, Yuxi. Very nice talk. And I have a few questions for the adaptive peak simulation there. So is the peak region you define initially how or it evolve with your simulation?
It depends on your requirement. You can keep it steady. If you want to capture the reconnection physics, then you may want to calculate how strong the current is and use the peak to cover the strong current area.
So you mean that peak region can evolve
Yeah.
at different times?
Yeah.
Another question is in more detail, just how does it go to finer grid scale? It is decided from your simulation results, such as gradient. You have a determinant factors to see, or if the difference between the two values is large, the gradient is larger than some number, you go to finer scale, right?
So are you talking about the AMR for MHD or MHD epic?
For the MHD epic.
So far for the MHD epic, we fix the grid resolution.
You mean the grid is already fixed?
Yeah. Yeah, but now we are developing AMR peak. It takes some effort.
The talk. So there are some things MHD does really well, or some things our low models do very well.
Mhm.
And some things they do well in a statistical sense.
Mm.
So for example, like a substorm, it's difficult to predict timing of one substorm, but MHD can say roughly how many will occur in a day.
Mhm.
As we look forward, get more sophisticated models, add more physics. Should we expect to ever be able to predict some of those more impulsive things, or are we kind of always just going to be able to do statistical capture of them? So like an FT is a similar thing.
Mhm.
Predicting the formation of one FT is really hard. You can get statistics of size and frequencies.
Thanks for your question. I think now Michigan group is trying to do some event study to see for a single event how good the MHD can match simulation. And this simulation result shows it may, for some period of the time, it may reach swell. But I agree, it's very difficult to match a single event like the substorm onset or dayside FTEs. But statistically speaking, I don't know how good they will match, but I think in the future more simulations will be done to do this statistic analysis. Thank you.
Thank you very much for the talk. I have a question about the heat flux. I've been hearing from multiple scientists that heat flux is very important, and I'm just curious your opinion on this.
To be honest, I don't know.
Anyone? So important so everyone can do the same page?
The electrons being free constantly go along. The electron thermal conductivity is enormous.
Plus is important for MI continuity or even big sphere.
In this high moment method, it is very difficult to find out a proper heat flux for your applications. But in the fully kinetic model, in principle, if you have proper parameters, this heat flux are already included.
Why the heat flux is important, right? For MI coupling, of course, it dominates it. MI coupling results from field line currents. What causes field line current? You have to have a divergence current equal to a plane. How do we get that? We get that by magnetic drift. Magnetic drift is energy dependent. Okay, so as soon as you have a pressure gradient, and the gas mutually in the plasma sheet, the divergence of particles due to magnetic drift, all those particles carry charges, so that's a divergence of current. That's how you generate the regions of current system. So the whole physics of the regions of current system, formation of free current, all that kind of thing, and everything that the open closed field line boundary involves the field line currents, which are generated by the divergence of the heat flux vector, which is due to the energy of the magnetic drift.
So much, very nice talk. I'm curious about the productive avenue. Can you talk about how you determine the region of the adaptive peak region? And what is the time resolution? Because I guess you will change your adaptive peak region from time to time. How do you determine this time resolution compared to the time scale you are simulating in every connection? And last question, how did this adaptive epic will reduce the memory requirement? We talked about previously.
Okay, thank you. So the first question, how to determine where the peak region should cover? So far, the adaptive peak method have been used to simulate a few storm events. Use the peak to cover the tail area, and we use current. Essentially, we use current to determine where the reconnection may happen. So cover that area with peak. If you want more details, you can search the paper by Xiantong Wang. He carefully described how we do the adaptation for the tail simulation. Another question, how frequently we change the peak grid? Ideally, of course, you may want to change it every step, but then your simulation may become slow. So in practice, we may decide how frequent these tail structures change. For example, how fast your flux, your tail plasmamoid moves. Based on the spatial time scale of the motion of this structure, you can determine how fast you want to change your peak domain. And in the adaptive peak approach, you only covers the region, the area where kinetic effects could be important. So the total volume covered by peak could be small. That's how we could improve the simulation efficiency and saving the memory.
You said that it invites extend moment method to light waves.
Yes.
Can you
do something like a Darwin approximation by splitting things into parallel perpendicular direction in order in those light waves to remove the CFL constraint you surely get from those light waves?
So could you repeat your question again?
Can you do a Darwin approximation, which
Uh-uh.
is correct to order d squared over c squared, and order out the light waves and take longer time steps?
Well, great comment. I do not have too much experience of developing this high moment method, so I don't know. But there is light wave since we solve the full Maxwell equations.
Thanks.
So you demonstrated the potential strengths of MHD. The embedding of a PIC code into an MHD code. Have there been any studies embedding moment methods or higher resolution, higher moment methods into more simplified MHD solutions?
This is a great question. I listed something here, but I didn't go through all of them. So far as I know, besides MHD EPIC, I think Los Alamos is collaborating with APL, try to embed their spectral code into global fluid code. And I know a group in German, in Europe, they are embedding a fully flat soft solver into a two fluid model. That's all the embed models I know so far.
All right, thank you again so much for a wonderful talk and a great discussion afterwards.